Okay, last time we talked about matrix multiplication. And the thing I'm like to emphasize about matrix multiplication is that you may have learned matrix multiplication in another context. For example, I learned it in Calculus 3. And it doesn't really, in another context, it often doesn't make any sense. When I learned it in Calculus 3, the instructor said something like, well, you do this thing and you take these rows and you combine them with these columns in this peculiar way, and we were all like, you do what now? So if you want to combine two matrices, why don't you multiply them the same way you add them, entry by entry, or some such thing. So we're all left with this sense of we're doing an operation that is hard to make any sense of. So the approach here, the approach in this chapter, is that matrix multiplication makes all the sense in the world. The definition of the operations makes all the sense in the world if you look at it the right way. And in fact, the point of the entire book, the point of many books, but anyway, the point of this entire book is that you can see the entire subject as a sensible whole if approached in the right way. It might be a way that's new to you, a way that you've never had the opportunity to approach a subject before, but it all makes beautiful sense if you think about it in the right way. Okay, so here's an example. This is the check-in for matrix multiplication, and you can see by looking at the question before we have a whack at it that we start off by looking at maps. Remember, we're taking maps to be primary. We start off by looking at maps, and then we represent those maps. We have a computational scheme for computing the actual thing, the map. And we want to, at the bottom, you see, we want to be able to compute the composition of two linear maps. Okay, so let's have a whack at it. This is kind of a long one. Let's see if I can remember the various parts here. So I have that h does what? H takes a plus bx plus cx squared over 2. The linear term will be a plus c. So you take the constant term. You take the constant term and the coefficient of x squared, and you add them together, and that's the constant term of the outcome. You double the coefficient of x, and you just leave the coefficient of x squared the same. Okay, so that's h. G is some other, basically also arbitrary. So a plus bx plus cx squared maps under G to, what do you do here? You take the coefficient of x, that'll be the new constant term, minus the coefficient of x, so you change the sign of the coefficient of x, and then a minus 3c. That'll be the coefficient of x squared. So it transforms polynomials, quadratic polynomials, into quadratic polynomials, and both of them do something that's not trivial. You've seen many times before, my way of picking examples is to pick ones that are not obvious, but that are not too hard either. And then I picked a basis. I picked the same basis for the input and output space of 1 comma 1 plus x comma 1 plus x squared. Again, a basis that's not trivial, but is also not too hard to do in your head. So I can do Gauss's method. I don't need to prove that. Okay, and then the first example, we pick some vector from the space, and it happens to be minus 2 plus 3x minus 5x squared. And literally just picked it out of the air. Just the first vector that occurred to me. There's some numbers that are not too small but not too big. Some positives, some minuses. If you compute h of v, okay, so let's see. So the rule for h is you take the coefficient from the constant term and you take the coefficient of x squared, and you put them together, and that's where you get the new constant term. So that's what's minus 7 from the minus 2 and the minus 5. You double the coefficient of x, that's double 3 to get 6. And the coefficient of x squared is unchanged. All right, and then when you go to compute g, you do what? You take the coefficient of x, that's the 3, so that'll be your new constant term. The new coefficient of x will be minus 3, and the new coefficient of x squared is the constant term minus 3 times the minus 3 times the input coefficient of x squared. So that's what, minus 2 minus 3 times minus 5, so that's minus 2 plus 15, so that's plus 13 x squared. Okay. Okay, then I'm going to take a g composed with h of v. So I'm going to apply g to this. So let's see, when I apply g to this, I have to take the new constant term is the coefficient of x. So that's 6. And the new coefficient of x is minus the coefficient of x. So minus the input coefficient of x, minus 6x. And then the new coefficient of x squared is the constant term minus 3 times the input coefficient of x squared. So I'm looking there at what? Minus 7 minus 3 times minus 5. So that's minus 7 plus 15. So I get what, 8? Okay. And then likewise, h circle g on v. I got to apply h to this. Okay, so let's see. How do you apply h? You apply h by taking the constant term will be the coefficient of x squared and the constant term of the input. So we're looking at 16. You get the coefficient of x by doubling the input coefficient of x. So that's minus 6x. And then for the coefficient of x squared, it's the input coefficient of x squared, 13. Okay? Okay. Next step, number 2, is to represent all these things. So I'll start by representing the vector. There's only one basis. I'm calling it b. You can call it d if you want, but I'm going to call it b. And the vector is up here, minus 2 plus 3x minus 5x squared. Okay? So the thing about this input basis is that I can do it by eye. I don't have to rely on Gauss's method. I'm not embarrassed by Gauss's method. If I can do it by eye, then I'll choose that. So you can see that only one of these basis elements has an x squared. So the representation must have a minus 5 down here. Only one of these 3 basis elements has an x, so the representation must have a 3 here. And if I'm going to take minus 5 times that and plus 3 times that, then in order to get a minus 2, I guess I need a 0 there. 0. Okay? And you can write a sub b there if you like, or you can leave it out if you like, because there's no question here what the basis is. Okay, next up is to represent the first map. So represent with respect to a starting basis of b and an ending basis of, I'm going to write bb. You can write bd if you like. It doesn't make any difference. Of h. So we've seen before how you do these. You take each of the 3 basis elements. So 1, see where it maps under h. 1 plus x, see where it maps under h. And 1 plus x squared, see where it maps under h. And let's see, this maps to what? You get 1, 0x, 0x squared. What does 1 plus x go? You get what here? 1, 2x, 0x squared. And where does 1 plus x squared go? You get here 1 plus 1 is 2. 0x 2x plus x squared. So it's 2 plus x squared. Okay, so the advantage of the basis is that it just saves me a certain amount of work when I do the representations, and so that comes out exactly here. So the representation with respect to the basis of the output, that one is this one right here, is I can do that by eye. So in order to get an output of 1, I guess I need 1 of these, 0 of these, and 0 of these. To get a representation with respect to b of 1 plus 2x, I need 0 of the third, 2 of the second, and then minus 1 of the first. So I'm sorry, that says minus 1, 2, 0. All right, and then to represent 2 plus x squared. And again, I could do Gauss's method, but I'm just, that's not the point of this particular exercise. So I guess I need a 1 here. There are 0 many x's, and so I need a 1 there to make up the 2. And so, in sum, the representation with respect to BB, or you can write BD, that's fine, H, is the 3 by 3 matrix. Put these three column vectors together, 1, 0, 0, minus 1, 2, 0, and 1, 0, 1. And it's natural to call that capital H. And last, the representation, same deal, only for G. So you see where the basis elements go under G. And let's see, this is going to be what under G. I need, A is 1, B is 0, C is 0. So I get 0 minus 0x, so 1x squared. So I get x squared. 1 plus x, I guess this is, for 1 plus x, this is, A is 1, B is 1. So I get 1 minus 1 and 1. So I get, 1 minus x plus x squared. And for 1 plus x squared, I guess I get, so this is 1, 0, and 1. So I guess I get minus 2x squared. Okay, and then the representations is again a matter of eyeballing the answer. What do I get here? I guess to get x squared, I got to have a 1, and there are no x's, so I got to have a minus 1. To get 1 minus x plus x squared, I got to have a 1 and a minus 1, and to make the constants balance out, I guess I need a 1 there. And then finally, to get minus 2x squared, I need a minus 2, and there are no x's, and so I guess I need a 2. You put them all together, call it G, call capital G. And you get a 3 by 3 matrix. Minus 1, first column is minus 1, 0, 1. Second column is 1, minus 1, 1. Darn it. I closed my columns too quickly. What the heck was I thinking? And then the third column is 2, 0, minus 2. And again, you can write a BB here, or you can leave it out if you think there's only one matrix in sight. Excuse me, only one basis in sight, and no one will get confused. Okay, so far, I started off by talking about the maps, and now I've at least started representing those maps. I have yet to apply them to the vector. I'll do that next. Need a fresh piece of paper. Okay, so let's see. For the fresh piece of paper, I'm going to have here that GH is, I'll copy them down because the old piece of paper is gone. Minus 1, 1, 2, 0, minus 1, 0, and 1, 1, minus 2. That was capital G. And capital H is 1, minus 1, 1, 0, 2, 0, and 0, 0, 1. Okay, so a person goes through the operations, and this is arithmetic, so I'm not gonna fret about it too much. Minus 1 times 1, 1 times 0, 2 times 0. Just to go through and do the second column, minus 1 times minus 1, 1 times 2, 2 times 0. minus 1 times 1, 1 times 0, 2 times 1. And again, it's arithmetic, so I'm not gonna bore you with the excruciating details. But just to do the first row, first column, 0 times 1, minus 1 times 0, 0 times 0. And one thing that we see here is that zeros are awfully handy in this context. And I'll fill in the rest. I've done this in advance because I can't rely on myself to get it right if I'm not relying on my notes. So 1, 1, minus 1, because arithmetic is not a strength of mine. And HG is, and again, I won't bore you with the details. It's the two matrices in the opposite order. And I got 0, 3, 0, 0, minus 2, 0, and 1, 1, minus 2. A person notices that they're not the same, but then a person notices from the previous page that GH and HG don't have the same effect, so it's hardly surprising that the two matrices are not the same. Okay, and then question 4 here asks me to calculate the representation. So question 4, the representation with respect to the output basis, I could say D, I'm saying B because I'm calling everybody B, of G circle H of V is you represent map application by matrix vector multiplication. So G circle H is represented by what's up here, minus 1, 3, 1, 0, minus 2, 0, 1, 1, minus 1. I forgot the vector already. What the heck is it? 4, minus 6, 8. No, 0, 3, minus 5. Sorry. 0, 3, minus 5. Sorry, lost my head. And here's where the 4, minus 6, 8 goes. 4, minus 6, 8 goes. So for example, minus 1, 3, 1 by 0, 3, 5. Minus 1 times 0. 3 times 3 makes 9. 1 times minus 5, and you do get the 4. If I take the representation with respect to the output basis of H circle G, you represent that by taking the HG matrix, 0, 3, 0, 0, minus 2, 0, 1, 1, minus 2, and by the representation of the vector, 0, 3, minus 5. This time you copy it down correctly. And when you do the, for example, 0, 3, 0, 0, 3, minus 5, the 3 and the 3 make a 9. So I'm looking at 9 minus 6, 13. Okay, and now I'm going to verify, so check. G circle H of V. Do you remember what G circle H of V is supposed to come out to be? 6 minus 6x plus 8x squared. So to see that it comes out to be what I want it to be, it's supposed to be 4 by the first basis vector, minus 6 by the second basis vector, plus 8 by the third basis vector. That's what representation means. And when you do the arithmetic, you get obviously 8x squared minus 6x and 6. Yay! And then the other one, H circle G on V. So it's supposed to be 9 times the first basis vector minus 6 times the second basis vector plus 13 times the third basis vector. So this represents, with respect to the basis, this represents, with respect to the basis, this thing, and I'm doing a verification that I do get what I'm supposed to get. What am I supposed to get, by the way? I'm supposed to get 16 minus 6x plus 13x squared. All right, well, the suspense is killing me. Let's see. So I see the 13x squared. I see the minus 6x. And the constant term is 13 minus 6 plus 9. So I get a 16. So yeah, so that's right. So the matrix multiplication computes the action of the of the function composition, the G circle H in this case, or the H circle G in this case. Matrix multiplication works the way it works, not cockamamie, sensible, works the way it works because this is supposed to happen. That's exactly why we made the parts of the matrices combine. They have to combine in some way. What way do they combine? Well, we went through and did an example. They combine in this certain way. That's the definition of matrix multiplication. It isn't what I saw in calculus, which was just some cockamamie thing that didn't, you do what now? No, it makes perfectly good sense if you lay out the parts in some organized way and then you see how they combine. They combine in this way. That's the definition. Okay. Okay, so that was the first part of matrix multiplication. Now today, second part of matrix multiplication. So let's see here. Last time we finished with the theorem that I mentioned has to be true because if it wasn't true, we'd change the definition of the matrix product. The theorem says composition of linear map is represented by matrix product of the representatives, and again, that was the point of the check-in, that if it wasn't true, I'd change the definition of matrix product. Matrix product is defined precisely to make this result come out true. Okay, so this is the point of this section. And in some ways, it's the point of the book. Point of the book is that it's possible to see these things on a computational level, but nonetheless, it's possible to see these things as all making sense. If it isn't making sense, there's something wrong. Okay, so now you've seen how we work many times before. Now what we try to do is surround the idea that in this section, in this case matrix multiplication, surround it by supporting material that helps a person make some sort of mental framework where it all hangs on, the concepts all hang on together. Okay, so here's an example of that, a mental framework. So this is a picture of what the previous slide says. The previous slide says if you look at the map composition, if you look at the map composition, H first and then G right here, you can get map composition in one of two ways. You get from V to W by doing H first, and then you get from W to X by doing G next. So this is, I'm describing the maps. And remember, we take maps to be primary. Or you can do the single operation, composition G circle H, which means do G after H. And now here, the purpose of the drawing is the purpose of the arrow diagram is to put the matrices in. So naturally, I'm calling the matrix representing little h by capital H. I'm calling the matrix representing little g by capital G. And so I'm calling the matrix representing G circle H by the matrix product G, capital G times capital H. You see I put in bases here. So the point is that if you're going to do composition, that the matrices reflect exactly the composition operations. So above the arrows, the map shows the two ways of going from V to X. You can go straight over via composition, or you can go up and you can go sort of diagonally up and then diagonally down. And that's just the definition of composition. That's what composition is. Below the arrows, the matrices show that the matrix product GH is how you go directly from V to X. You can go from V to W via H, and then from W to X via G, or you can go straight from V to X. You can do your computations straight from V to X via the matrix product GH, and that bottom line is what this says, that the representation of G circle H is GH, and that's the same thing, GH is the same thing as the matrix product of capital G and capital H. And obviously an example, and this example looks a lot like the check-in. This example, like the check-in, is the key idea here, is that matrix multiplication makes sense. It isn't some cockamamie thing that nobody can understand or some act of genius. It all makes sense. It all fits together. So I have three spaces, R squared, P2, and the 2x2 matrices, and of course I chose three different spaces because I think that helps a person figure out where we are at any moment. I have H from R2 to P2 and G from P2 to M2x2. And you've seen me make many examples before. I'm just simply here making up examples that are not too hard and not too easy. The composition does this. The composition takes in two tall vectors and puts out 2x2 matrices. So G circle H takes in two tall vectors and puts out 2x2 matrices. And I'm just going to compute the representations of all that stuff. So the representation here, the representation of H is right here. I figured out where the basis elements went. I represented them with respect to the basis, the output basis, in this case the basis in P2. And there we go, we got H. I do the same thing for G. Figure out where the basis vectors go, represent them with respect to the codomain basis, and I got a matrix for G. To figure out what the composition is, you have two choices. You can either see where do the basis elements of capital B go, where the basis elements of the input space capital V go, and then represent them with respect to the output basis, and that's what I did here. Or you can multiply the two matrices that we got on the prior slide, and of course you have to get the same answer. So said again here, I know being repetitious, but nonetheless, it's a big point. The representation of the composition is the matrix product, don't forget to get the right order, is the matrix product of the representation of the individual maps. And that's the reason for the definition of matrix product. So that arrow diagram, I think, helps a person put down the where does everything go and where do the spaces sit. I'll make another point about the order in which you write the things, is that we write a composition as G circle H, even though G is written first. G comes, if you read it left to right, G comes first. But in fact, it's the map that it's applied second. So when you do a map application, you go from V to H of V, that is, you apply H first, and then you apply G to that. It's just like in calculus when you write something like sine of x squared. You do the x squared first, the part inside the parentheses. You do the x squared first, and then you do the sine. Well, so too here when you write G of H, you do the H part first, and then the G. And that order carries over to the matrices. So G circle H is represented by capital G, capital H. Very easy to flip it around. I know a person is thinking about a dozen things, but that's the right answer. Is that capital G, capital H represents G circle H. We saw that on the check-in also. Some dimensions here. So the input space is N, and the output space for the composition is M, and the intermediate space is R, dimension R space. H takes you from a dimension N to a dimension R. G takes you from a dimension R to a dimension M, and that makes the matrices have these sizes. M by R, R by N results in the composition being represented by an M by N. Briefly, if you write down the sizes of the matrices, you see that 3 there and that 3 there. It's like those two threes, that pair of threes. It's like they kind of cancel. Of course, they don't cancel, but it's like they cancel somehow. And what's left is a 2 and a 4, and that's the answer. You can see the 2, 1, 4 can combine with the 3, 5, 1 to give the 15. So the sizes match up in the right way. Very important observation that we already made with the check-in. I observed it, but I passed over it very briefly. But want to make that point more strongly here. Matrix multiplication is not commutative. Cosine of square root of x, function composition in general is not commutative. Cosine of square root of x is different than the square root of the cosine of x. And that turns out that function composition is not commutative, holds even in the special case of linear functions. So just as an example, I wrote down the first pair of 2x2 matrices that occurred to me and multiplied them in opposite order and didn't get anything like the same result. Matrix multiplication is not commutative because function composition is not commutative. And so naturally, as with the check-in, the compositional aspects of the maps represent the fact that the underlying maps don't commute. Here's another example, maybe a more extreme example. These two, you can multiply them in one order, namely the order I wrote them. 3/4 by 8 minus 4, that you can make sense of that. But you can't multiply them in the opposite order. If you tried to put 8, 12, 0 and do the dot product with 3, 0, you're in trouble. There's not the right number to match up. Okay, so matrix multiplication is not commutative. So there are some facts that you can observe about matrix multiplication that you can observe them as being consequence of maps, and that's always our go-to. But you can also observe it just as a consequence of how the parts combine. Although matrix multiplication is not commutative, it does have some reasonable algebraic properties. For example, it's associative. FGH is the same thing as FGH. It's also distributed over addition. F by G plus H is the same thing as FG plus FH, and likewise on the other side. Those matrix operations, you can understand them in terms of the underlying parts by looking at a lot of index i's and j's, but it's really much easier to understand them as being a consequent of the map fact. Just as an example, matrix multiplication is associative because map composition is associative. F circle G circle H is the same thing as F circle G circle H, because both of those maps send V to F of G of H of V. And distributivity is just the same thing. So the matrix the matrix computations represent the underlying map facts. Literally, if something is true about the maps, it carries up to their representations. Okay, when we come back next time, then we will look at the ways that matrix multiplication, the way that the parts of the matrices combine. We're not too proud to get down in the matrix and say this part matches up with that part. Sometimes you can learn things from that, and that's what we're going to do next time. Okay, so we'll see you then next time. Very good.